This meeting is being recorded.
All right, you're good.
Hello, welcome to our fireside chat number 6. I hope you've been enjoying these. They've been a lot of fun for us to produce and to bring to you. Just as with all of the fireside chats, we record this. And the previous ones, there are 5 of them. The previous ones are posted on Coursera. You can find it in the resource tab. And the recording from this session will be posted there shortly. Just a couple of reminders. There are probably some new faces in the fireside chat today, and that's great. But your microphones are muted and the videos are turned off, so please don't turn them on. And so typically the way we run these is we have a presentation and we have a guest today who's going to be involved. And when we get finished with that, if you have a question that you want to submit to either to me or to our guest, Ray Hill, then please do that with the chat function on the Zoom menu bar. So you don't need to wait until the Q&A part before you start submitting the question. You feel free to do that at any time. And if your question doesn't get answered before we have to wrap up in an hour today, then we'll take those offline and try to get them answered and respond to those questions in Coursera for the people that are enrolled in the course. I'd like to thank a lot of the people involved in helping to put this on. Here at ASU, quite a few people have been working hard to make this MOOC a success. Scott Muller, Tom Arcuse, who did a lot of the supervision of the original recordings, Carly Metcalf, who did the recordings for JUMP, Amy Kitchens did a lot of work on the course design, Dustin Hampton did a wonderful job building this set. Megan Gibson handles so many of the operational details of this, and all these people have just done a really wonderful job with the course. I mentioned that we have guests, and today our guest is Dr. Ray Hill. Ray is a professor of operations research at the Air Force Institute of Technology, or AFIT as it's known. He's a retired lieutenant colonel from the U.S. Air Force, and he's been working in the academic world for 23 years. His research focus is applied statistics and experimental design, and among his responsibilities at AFIT, he runs the graduate level certificate in test and evaluation. And this is a very rigorous 20-hour graduate level program on statistics and experimental design. And it's for the Air Force test and evaluation workforce. And he's been working very hard for quite a few years to bring rigor and good statistical practice to the way test and evaluation is done in the DoD. Ray has over 100 journal papers, over 250 total technical publications. He's been involved in over 300 graduate projects. These are master's theses and PhD dissertations and other types of projects. He's currently the editor-in-chief for military operations research and for the Journal of Defense Analysis and Logistics. And how he manages to be a chief editor for 2 different journals and not go crazy, I have no idea, because I'm the chief editor, one of the chief editors for a journal, and just one drives me crazy, and I have 2 other chief editors to share the workload. So how he does it, I don't know. He's great. But he's also an associate editor for the journal Quality Engineering. So Ray is a busy guy, and I really appreciate him taking time out of his schedule to spend time with us today. And he is going to talk about the use of statistics and experimental design in the DoD community. So Ray, thank you very much for being a part of this, and you're on.
Thank you, Doug. I'm going to go ahead and okay, so I assume you can see what's on the screen?
I got it.
Good. Well, thanks again, Doug. As far as being crazy, please don't poll my students. They're apt to give you an answer I don't want to hear. But I do thank you for this chance to share some thoughts and some of my experiences regarding experimental design, statistical rigor. This has been my focus area for probably the last 12 years, and it's been nothing but eventful and fulfilling. So what I've got in today's pitch is to focus a little bit on my objective in this area of experimental design, statistical thinking, which is to try to maximize the information that we get from an experiment using the resources expended for that experiment in some most efficient manner. And the way I want to do this is to focus on 4 examples that I've been involved with. These are all examples involving some of our master's and PhD students, all of whom are Air Force officers, that highlight the benefits of taking a statistical approach to thinking about the problem and developing the experimental design. I'm going to make these overviews necessarily terse, but I do have details of these in journal papers with references provided at the end of the talk. So the first one is using these methods to improve an experiment and the experimental processes that are involved. And in this first example, we were supporting something called live fire test. Live fire test is what it sounds like. It's actually shooting objects at other objects. In this particular case, we're shooting small metal objects into steel plates to mimic what happens when you have ballistic flashes. Our focus in this was on an area called survivability and vulnerability, specifically of aircraft. In the Air Force, we try to make aircraft survivable. That's a very good thing if you're the pilot. We want them to have reduced vulnerabilities, be very robust to attack. When missiles are fired at aircraft and explode near the aircraft, they send fragments into that aircraft. These fragments are traveling at high velocity, and their impacts cause not only penetration into the aircraft, but they can cause flames. And those flames could be on the outside of the aircraft, or more critically, on the inside of the aircraft. And really what we want to do to be able to build more survivable aircraft is have a model of that flash event. So what we were doing is working with people in the survivability world to try to build such a model. This graphic shows our focus. The graphic at the top, going from right to left, shows the impact into the panel, which is the dark blue rectangle there. The flash, the penetration in the middle panel with a flash after penetration. And note that, and then down below that is a picture of an actual flash. So that's an actual impact event where you see the impact on the right side, the penetration, and the subsequent flash on the left side. And what you see on those pictures are a green ellipse. We're going to use that ellipse to be able to collect our data. So what we do is we take these high-speed photos of the entire flash process, encapsulate the flash in an oval, ellipse, and then we can measure that ellipse along its major minor axes, as well as its distance from the impact point and the direction, and use this time series set of data to build an empirical model of that flash. That was our goal. We're going to take this analysis data and build our model. The problem was their setup. Their initial experiments had some problems. The ellipse sizes were developed via MATLAB code, and the MATLAB code was based on model parameters tunable by the analyst. Well, the analyst wasn't a statistical guy. He was a mechanical engineer flash guy, and they would change the parameter settings to make the ellipse look bigger so they could get a better view of the flash, which of course made the data heteroscedastic, it was non-constant. So we had data that we couldn't use. Furthermore, the initial setup had the camera a little too close. In other words, we had flashes that filled the whole screen. They weren't measurable. Such flashes were fine if you're the survivability guy because you like those flashes. They're no good because now they're truncated data. So it ended up our initial set from this type of design setup gave us bad data. So what we tried to do was change how they set up the shot lines, the red line, change how they position the camera near the test panel, and subsequently change how they did their analysis. And this is what happened. The initial approach that they used, we only got about 33% of the observations were usable, a 66% data loss. You never want to run experiments where you're throwing away 2/3 of what you're doing. So we helped them refocus the analysis, redesign that setup, and our results were that over 80% of the shots that resulted could be used. And moreover, we ended up having shots that span the entire range of velocity, shot size, angle, all the factors that we needed to be able to produce a model. And we ended up producing a model, delivered that model, first ever model, and that model is now implemented in the survivability tool. So a great case of using statistical thinking to just improve the setup and improve the efficiency of that setup. My second example is how we can use these modern experimental designs to be more efficient. And this is actually some work that I've had the pleasure of working with Dr. Montgomery on. It's focusing on wind tunnels. So wind tunnels are extremely crucial when you're dealing with aerospace systems. And the Air Force, of course, has lots of aerospace systems, aircraft, missiles. We need wind tunnel data to be able to characterize these systems. So our focus was on how to examine changes from the current legacy approach to wind tunnels, which is to take one factor at a time and vary it across a sweep. And look at instead the use of modern design approaches as a way to improve the resources. The problem, of course, is that there was concern that there would be information loss. We're going to move away from what they've been doing for 30 years and do something new, and they're not going to get the information loss. So our approach was to examine if we could do things more efficiently and try to quantify the information loss. So again, these OFAT designs, as we know from this particular course in design of experiments, are not particularly efficient, but they are the legacy approach to wind tunnel testing. They've been doing these for years, and the people running it are not real open to changing what's been successful. So our modern designs are quite run efficient, but we don't have a way to quantify the information loss. So this study was to try to do just that. So our focus in this particular work was to compare those legacy OFAT designs to modern designs, see how much we can reduce the designs, and quantify the information loss. Well, it's kind of hard to quantify the information loss, but we came up with a pretty neat way to do this. We were using some data produced by the Arnold Engineering Development Center, AEDC, which is located in Tennessee. They have huge wind tunnels, been doing this stuff for years. This was data from a missile drone system that was worked some years back. And the data, you can see the ranges there in different ranges of performance, approximately 9,000 runs. So as you might imagine, this was a very large wind tunnel campaign. Our approach was to consider some modern designs, and these are designs that, having taken this course, you're familiar with, the eye-optimal designs, essential composite designs, nested face center designs, which were have been used in wind tunnel testing. One of Dr. Montgomery's colleagues, Jim Simpson, has done a lot of work in that area. So our approach was the following. We're going to go ahead and take those 9,000 runs and build a surface, a response surface of that. We're going to call this the true model. We're then going to sample from that surface with the design strategy from one of these modern designs. and use that reduced data set to fit another surface. And we'll call this the model surface. And then we're going to determine whether or not these surfaces are sufficiently equivalent. If they're sufficiently equivalent, then we can get the same surface from fewer design points. We don't need all 9,000. The amount that they differ is the information loss. Now, the full study examined these things in 3 ways. We looked at them graphically, sort of a visual display, and I'll show you an example of that. We looked at them statistically, doing comparative sampling, and I'll show you some of that. And we also compared the resulting regression model in terms of the coefficients. I'm going to refer you to the detailed references that are in the back of this presentation. So let me go ahead and show you the graphical comparison. I can't give you the actual indices or the actual axes because, again, this was a DoD system, but realize that we've looked at 6 factors across all the ranges. The blue surface is the true surface, the green surface is the reduced sample surface, and you'll see that other than at the edges, these surfaces are pretty much aligning. This is very good. This means we don't need 9,000 runs to generate the surface. We can get by with a smaller amount. So that's graphical, give us a good intuition, but we want to do things statistically as well. So we took the true surface and the reduced data surface, sampled the surface randomly over 10,000 points. That gave us a nice paired t-test. We took this paired t-test to determine whether or not these surfaces are significantly different. And what we found is that they agreed quite well. So you'll see here that while the means don't fall, or these confidence intervals don't fall around 0, they're pretty close. So there's no real information loss here. So what we found is that we could, in fact, reduce the sample size. We demonstrated this reduction. In fact, we demonstrated a 90% reduction. We could take this design from 9,000 data points down to about 900 and not really degrade the information as measured by the surface in doing that. This was very insightful. The AEDC folks were quite happy with it, but this also raised the question was, could we go even smaller? And this is where Dr. Montgomery came in, because he asked one day at a meeting that we're at, hey, this is interesting, but how small can we go? So in part 2, that's what we looked at. We looked at, can we consider smaller designs? And when we do that, how much smaller can we go? So this particular study, which you can find in the Quality, Reliability, Engineering International Journal, got down to about a 98% reduction. Now, when we got down that far, we had a little bit of concern about the surface, but at 95% reduction, sample size of 312, down from about 9,000, we still had, basically the same amount of information. So we could reduce this wind tunnel size down about 95%. Now, this means you can do things quicker, you can do things in a more randomized fashion, and do things a little bit more efficiently. So real nice study to look at and compare and demonstrate the viability of using these modern designs to be more efficient without generating less information. My third example is going to take this idea of information and say, can I use modern designs to generate more information? Again, my objective, maximize the information while minimizing the resources involved. And in this next example, which was done at the Air Force Institute of Technology through joint work with the Aeronautical Department, Mr. Tim Cleaver, along with Dr. Alex Gutman, helped lead this. We had the opportunity to get involved in a computational fluid dynamics study of a conceptual missile system. And in this particular case, got to actually compare side by side the legacy approach and the modern approach. And the motivation was to look at this highly maneuverable missile. I'm not going to name the missile or the company that's building it, but AFIT was involved in some of the analysis. This is a missile that'll go off rail, turn 180 degrees and fire backwards. So again, high maneuverable, We're using computation fluid dynamics to investigate these. And in this particular case, we were looking at how would we design the experiment to run this computational fluid dynamics code in a very efficient manner. Well, we came up with this design, which ended up being a space filling design. And the engineer had concerns that, well, that's not how we do things. We're going to not get the information we want. We've got to do the one factor at a time sweeps. Ended up, we did both. We did the sweeps and we did the space filling design. The space filling design looked like this. It was a Latin hypercube space filling design. These are covered in Dr. Montgomery's Design of Experiments book and his Response Surface Method book. These are the factors, looking at the 4 factors. This is the design space. I'll show you what the design looks like in a little bit. The point to keep in mind for now is that this space filling design involved 23 design points over this region. The one factor at a time sweep, this is the sweeps that they had to run. Again, this is the legacy approach. And the key point to keep in mind here is that this involved 79 runs. So the space filling designs, looking at these 4 factors, 2 at a time. This is a jump scatter plot, shows you that this Latin hypercube design does a real nice job of filling that space. Again, 23 runs looking at these 4 factors. Okay, so 23 runs versus 79. Let's take a look at the output. I've got 3 slides on output. I'll go through the first one in a little detail, but the other 2 follow similarly. This is the lift response. If you look at the upper left, you see the lift response curve. This is what the engineers like. This is what they want. The blue line and the dark, they look like circles probably. Those represent the OFAT, and as opposed to the space filling, and you see that there's nice agreement there. So they have this nice curve. That's what you get with the 79 runs. The lower right is what you get with the 23 runs. You get the entire surface. That curve is just one piece of that surface. So for this lift response, we could get the curve using the OFAT, or we could use the modern design and get the entire surface, which that one curve is just one small piece. And we can do the same thing for the other responses, in this case, drag. That's the second response. Same sort of thing. The OFAC gives us the curve. The modern space filling design gives us the surface. And finally, in terms of pitch. Now, what I like about the pitch is that you see that that surface varies quite a bit. So we can get that curve, but it doesn't represent what you see across the surface. But takeaway, in each case, the legacy approach over almost 3 times the number of runs gave us a curve. The modern design, very efficient run-wise, gave us the entire surface. So the key takeaways, 23 runs, we generated a lot more useful information than the 79 runs with the legacy approach. So again, this is a case where these computational fluid dynamics, very resource-intensive process, we can do things more efficiently and a lot more effectively by thinking about the experimental design beforehand. So looked at how do you statistically think to improve the design, make the designs more efficient without information loss, and then make the designs efficient with information gain. My final example is another example that we worked in conjunction with Dr. Alex Gutman again. This is where we're going to use these experimental design approaches to actually replace a model that's used, but just kind of resource intensive. The motivation or the focus of this was on a simulation model for jet engine depot repairs. Again, the Air Force has lots of aircraft. When the engines break, they have to be repaired, but engines that are in repair processes are not helping us operationally. So these particular engines are the engines built by, I believe, Pratt & Whitney, and they power the F-15 and the F-16. These engines undergo repair, during which time they're not available. This model built by Air Force Materiel Command, the analysis shop, looked at the supply chain aspects to get the depot, the material they needed to get these engines repaired as quickly as possible. The model output, the model results are desired by the headquarters and the depot and the 5 locations that feed these engines to the depot. Unfortunately, the model takes a bit to run. It has to be handled by the analysis, and oftentimes these locations don't have the simulation software. So our goal was to build a quick running tool to replace the simulation. We're going to do response surface methods. What we're going to do is run the simulation over the design region, use the responses to build the meta model. Now, we're not going to try to find operating conditions. We're going to use the meta model as a way to act as a proxy for the simulation. We're going to take that meta model, this regression, embed it in a spreadsheet model, which we can then give to the depot decision makers as well as the 5 location decision makers. It's quick running, it's available, and it would represent the simulation. The problem, of course, is that this meta model is going to be a little complex. Turns out the meta model needed to be at least a quadratic level model. There's a lot of factors. This would be a very complex design, but again, using some modern designs, we looked at definitive screening designs pioneered by Brad Jones from JUMP and Chris Notstein from Minnesota, and looked at this design and were able to get a run design in just 49 runs to examine the 24 factors and use that to fit this quadratic level model. I mean, that's a very efficient design. And what's really important is that the resulting meta model did a very good job of mimicking the simulation. That meta model was then embedded within the spreadsheet tool. You can see all the factors here. The bases, I misspoke, there were 6 bases. So you see the depot input, you see the base factors, base 1 through 6. I can't tell you the bases. You put the parameters in, and the meta model gives you the output that you would have had from the simulation. Classic example of using response surface methodology to build quick running decision support tools. So in this particular study, we showed how experimental design could really be used to just enable greater information sharing. We could summarize the information that you would have got from this simulation model, save these 6 locations from having to buy the expensive software to run it, and it provides a decision support tool that they needed. So again, 4 quick examples to highlight my key points that thinking things through from a statistical standpoint, statistical thinking can be extremely valuable. These are engineering applications as well as Department of Defense applications. Thinking about it can save you resources, get you a lot more bang for the buck, and avoid problems. As a wise person once said, all experiments are planned. Some are planned well, some are not. I like to say that all experiments have this statistical basis, and if we think about things statistically, then we can oftentimes do things a lot more effectively and efficiently. And the 4 data points I have were selected to try to show those. And then finally, we can promote efficiency and effectiveness, which is what we're all about. The 4 cases that I covered today are in these particular references. The publications, the first one, and then the 4th one covered the wind tunnel. The ballistic impact flash that I showed you is the 2nd reference. The side-by-side comparison is the last reference. And then, I'm sorry, the 3rd reference. And then the meta model is, of course, the last reference. These are all available in QREI as well as quality engineering. So with that, that's pretty much the time I had. I'm going to turn this over to Doug and see if there's any particular questions.
Okay, thank you, Ray. This was a very, very nice very nice examples. I'm very familiar with 2 or 3 of them, but these were all extremely interesting. And now we're hitting the Q&A portion of this fireside chat, and we already have a few questions that have come in. They were submitted prior to the start of today's fireside chat. So what I'm going to do is I'm going to read these questions and then talk about the answers. And Ray, please feel free to chime in and add whatever you would like to these to the answers that I'm going to try to go through. So this first question says, how would you treat a factorial design where you have 5 levels of a blocking variable? And this variable is apparently some position in a heat sealer that can seal 5 units or 5 products at a time. And you've done a power analysis, and the power analysis says that you need 20 runs. I'm going to assume that's 20 runs, not replicates, but 20 runs to achieve the desired power. Could you group 4 replicates of the same block for each treatment, and you want to eliminate the variability that might exist due to position from in the machine from the air up? So there's a couple of ways that you could approach this problem. This is, first of all, I've never seen this particular tool, and in order to get a really detailed, exact answer to this, I'd probably have to know more about the tool and about how it works. But I could give you a couple of general approaches that would be possibly appropriate. One possibility well, first of all, standard design is probably not going to work here. There's probably not any standard design that fits this problem. So this is going to be a custom design, what JMP calls a custom design, and probably a de-optimal design would be the way to go. And so one possibility would be to set up a design that has 4 factors. I'm guessing. Let's say you have 4 factors that are not the blocking variable, and maybe they have 2 levels each, and then specify a blocking factor that has 5 levels or 5 blocks, and then create a de-optimal design and see if that works for the problem. Now, hopefully that might be a design that you could run. I did a little bit of playing around with JMP yesterday, thinking about this problem. And you can create a design that has, it looks like 20 runs. So that would be one possibility. Now, the other approach, which would be a little bit easier to do, but still I think this would be an optimal design, would be to put, let's say, your 4 design factors in at 2 levels, and then specify an additional factor that is a categorical factor at 5 levels. That's the position effect. Then you could set up a model that has the main effects and the 2-factor interactions of the first, let's say, 4 factors, okay? And then only the main effects of the categorical 5-level factor. That effectively forces it to be a blocking factor. So you could set up the design that way and see how that looks, how that works. One of those 2 approaches would probably be a good start at thinking about how to do this design, how to run this experiment. And you should be able to do all of that in JMP. I did, as I say, a little bit of playing around with JMP yesterday in my spare time, and it looked like I could create designs of reasonable size with both of these approaches. And I hope that gives you some idea. Now, the feedback to the person that asked this question, think about what I've suggested here. And if you want to talk about this a little more and dive into more details on this, I would be glad to do that. But we probably have to have an offline discussion, because I'm going to have to know more about this tool and how it works and how many factors you've got. But I'd be glad to try to give you some insight on that. And so maybe the thing to do would be to try to contact me after today's session, and we'll see if we can figure out how to do that, either by email or by Zoom or by something. Okay. So this is a very good question, and I really appreciate it because it's clearly a real experiment that needs to be done. And there are some different approaches that could work. And it's also an example of a problem where standard design tools don't exactly work. And that's where these optimal designs come into play. Okay, here's another question. Is there any software which will help me in designing experiments in Indian context? And I'm struggling a bit to understand exactly what we mean here. Is this a language issue? That is, you want software that is written in a specific language, maybe some language that is spoken in India, for example. I don't know. I'm only familiar with JMP English version. There may be versions of JMP that are written in other languages or available in other languages. You could probably contact JMP and find out. Other software manufacturers that would be useful. Minitab is a very nice product. There's another product called Design Expert that is extremely good and very, very useful. And then there's a package called Stat Graphics that I'm familiar with. And so those are 4 packages that I know of that have good experimental design capability. And if you wanted to explore the possibility of are these packages available in other languages, you'd have to talk with the companies that make them. Again, I may have missed the point of this question. And if I have, please, contact us, and I'll try to answer the question. But I wasn't sure exactly what I was trying to do here. So now here's another very general question. How do I design and analyze experiments for a nonlinear kinetic model for catalytic reactions? And can we use JMP to do this? And the answer is yes. If you are using JMP and you open up the custom designer, you will see, or they open up the design of experiments tab on the toolbar, you will see that there is an option down toward the bottom on specialized designs. And if you open that up, one of the options there is nonlinear designs. Now, the way you do this is a little different from what we've talked about before. What you actually have to do is write the nonlinear model into JMP. You have to create that nonlinear model into JMP, and you do that following the information in that particular tab. JMP has some very nice examples of how to do this sort of thing. And so what I would suggest that you do is that rather than try to show you all the details of creating the model, go take a look at the JMP website and check out how to create a design for a nonlinear model. And they'll walk you through the process of doing that. And if that's too complex, if you're having trouble figuring out how to do that from the JMP website, let me know. And I can either help you with it, or I can put you in touch with someone at JMP that would be able to answer all of your questions about this. I do know some really knowledgeable people at JMP that I think could be useful in guiding you through this. But generally, if you have a if you have a particular nonlinear model, it is definitely possible to design an experiment for that particular model. So you can, and some nonlinear models are actually built into JUMP, but I suspect that what you want to do might be a very customized kinetic model. Good question. Okay, a basic question about measurements. We want to test one factor with two levels, let's say drug A and drug B, and not all participants will take the drugs, okay, responders and non-responders. And we want to measure the performance, such as the blood pressure level of the responders. Is it a valid comparison to compare the performance of only responders of drug A and drug B? Well, I think that's the only thing you can do, as I understand the question. Now, if all participants take both drugs, then you can do a paired t-test. If that's not the case, then you have a two-sample t-test. And what I would try to do is to design that experiment so you have a different group of responders with drug A and a different group of responders with drug B. Now, you may have other let's call them covariates, because the response might be a function of age, might be a function of gender, might be a function of weight, might be a function of other conditions. And so you would want to have that information available for each subject. And then you would end up probably with some sort of model that attempts to incorporate all of those covariates in the analysis. Because my guess is that the blood pressure is probably a function of some of these other parameters as well. Certainly we know that age and weight are things that impact blood pressure, and it's certainly possible that gender would. It's also possible that maybe other physiological or biological parameters could be of importance in this study. Okay. How long have these types of methods been used by the military? Is this a recent change? Ray, you're probably much better equipped to answer this than I am.
Sure. I mean, as far as experimental design, it's been used for many years. The Army has had a long-term conference on Army statistical methods. The Holloman test track, where they do the high-speed testing, has been using these techniques for years. As a matter of fact, if you've heard of Murphy's Law, that emanated from some engineers out at the Holloman test track. I think the emphasis started changing in the late 90s. The National Research Council published a book called Statistics, Testing, and Defense Acquisition that really called for methodological improvements. Part of those improvements actually referenced Dr. Montgomery's work on doing design planning. As a matter of fact, their book, Statistics, Testing, Defense Acquisition, if you look at one of their chapters, and I'm not sure if this is coming up on the screen, it references Dr. Montgomery's book. The real emphasis came about around the 2005, 2008 timeframe, when Dr. Mike Gilmore was the Director of Operational Test and Evaluation at OSD. And he's really the one that focused testing on things like statistical power, like hypothesis testing. And as a result, at about the 2012 timeframe, the Stat Center of Excellence was stood up here at AFIT under the leadership of a good friend of mine, Dr. Darrell Honor, a good friend of Dr. Montgomery's as well. And they go out and help all the major acquisition programs across the DoD implement statistical thinking early in their process. So I would say the answer to your question is that we've been using these techniques for years. We're becoming more cognizant of their power over the last couple decades. And part of the test and evaluation certificate program that I run, that Dr. Montgomery mentioned, is specifically to increase the technical cognizance in the T&E workforce on these statistical methods. So we cover empirical modeling all the way through advanced response surface methods, including optimal designs. So hopefully that answers that question.
Ray, you might want to say a few things, if you can, about our Science of Test Research Consortium involving the different universities, because I think that's another thing that is going on to support the kinds of activities that the DoD does.
Sure. Yeah, in fact, prior to the stand-up of our Stat Center of Excellence run by Dr. Honor, there were a group of us, Dr. Montgomery from Arizona State, Dr. Vining from Virginia Tech, and myself, and Dr. Rachel Silvestrini from the Naval Postgraduate School stood up what's called the Science of Test Research Consortium, funded by the highest echelons of tests in the test world. That expanded quickly to include North Carolina State and Allison Wilson, Florida State with Eric Chicken, and Arkansas with Dr. Ed Pohl and some of his colleagues. And what we've been doing for the last 12 years now is advancing the state of the art in experimental design methods, reliability measurements, reliability planning, and applied statistics. And that's been a great benefit. Matter of fact, that consortium, along with my T&E certificate program, really helped solidify the need to bring the STAT COE to AFIT under the direction of Dr. Honor. And I want to say that they're supporting 45 to 50 major programs a year. In fact, the Navy, I think their philosophy is you don't press forward until you touch base with the STAT COE and Dr. Honor's group. So the Science of Test Consortium has been a huge success. Lots of journal papers, lots of PhD students, a lot of people working in the test area. Great success.
Yeah, it's been a very, at least from my view, a very good program, because the funding supports doctoral students. Right. And some of those doctoral students have ended up going to work in the test organizations, and helping to transfer that technology into practice.
Yeah, we've had 3 of those students come work here at AFIT in the STAT COE. We've had a couple students work at the Institute for Defense Analysis, directly supporting the highest echelons of test. We've had other people that are down in the weeds in the test program. We had one colleague of mine, Lieutenant Colonel Brian Stone, worked with Doug at Arizona State. He's now working with the Air Force Operational Test and Evaluation Center. So again, great success. It all sort of feeds together, helping the DoD do things more efficiently and effectively.
And I think one thing that's promoted the success of this is we have tried to interact with the people in the test community to actually understand what their problems are, so that we can direct research toward things that actually hit where they have a need. Sure. And one of the things that's been very helpful in that is the conference that's run every spring in Washington, D.C. that the Institute for Defense Analysis puts on. Because we get people from all across the defense community, and NASA as well is now involved in this. Right. And people from the research consortium routinely attend that, and it's a great opportunity for all of these folks to interact and talk about, what's the latest problem, what are the things that are causing you pain, and that helps focus the research in a very applied way.
Yeah, all 4 of the examples I touched on today were sponsored under the Science of Test Research Consortium. I point interested readers to a special issue in the Quality Reliability Engineering International that focused on the science of test. And there's actually another issue coming out here fairly soon. Yes. Run by one of our PhD students, graduates of this program. She was a Virginia Tech graduate, and she's been special issue editor working with Doug to get that out.
Yes, that special issue is in the works, and I am hoping that it'll be published early 2021. The papers are sort of completing the review process and revisions, And I had hoped we might get it out in 2020, but I think it's going to be early 2021 based on what I know now. Okay, so I think that's the end of our questions that have been.
There's one more here, real quickly. They said, were they able to reduce the repair time of the engines provided by Pratt & Whitney as a result of the experiment? I would say I would have to categorize it. You probably can't reduce the repair time, but what you can do is reduce the wait time for parts. So part of the depot repair is not just the repair, but waiting on stuff. It's amazing how many processes in the DoD are impacted by dead time. For instance, pilots and Doug can relate to this, take about a year to train them. Well, they spend about 6 months waiting for training. If you have engines waiting for parts, that's dead time. So we're not going to change the repair time, but we will hopefully change the end-to-end time.
Cycle
by
time.
getting the parts there in time.
Yeah.
To do the repairs.
Yeah, you'll shrink the cycle time.
Exactly. Yeah.
From the time the engine goes in till it comes out.
Correct.
Yeah, it's hard to actually change the time required to actually repair the engine.
Right.
Although, there may be some things there that you could look at in terms of, the old, some of the Japanese techniques, single minute exchange of dies, SMID.
And there's a whole area of expertise pioneered by the folks Boothroyd and Dewhurst up at Rhode Island.
Yes.
Design for manufacture, design for assembly.
Right.
I'm sure those have been used in the design of these engines to some respect, but that's way outside our bounds. I'd point you to some of the folks up at Pratt & Whitney. They have an amazing analysis group up there. They've been leading edge of some of this new statistical thinking and statistical engineering. So Chris, I'd point you up to the Pratt & Whitney folks.
Yeah, that's probably a very good reference for some of that. But I know that there is a lot of work in terms of design for even designing systems so that they can be easily repaired. Something as simple as the automobile industry has done a lot of work in that area. How to design a vehicle so that it can be repaired easily. Yeah. And looking at common failure modes, and they've some of the car manufacturers have done a pretty good job of that.
Yeah. So Boothroyd and Dewhurst focused on design of assembly to start, but now there's design for just about anything. It's actually called design for X. Google design for X, you'll find a whole bunch of things in that area. Right,
and that's a good source. So it looks like we are down to just a handful of minutes left, but no more questions. But you can continue to submit questions, and we can deal with them later offline. The next Fireside Chat is going to be on Wednesday, November 18th. And we have a special guest for that session as well, and you're going to really enjoy him. It's Dr. Steve Rigdon, who is at St. Louis University, and he is the co-author of a new book on statistical methods. Now you're going to love this. Statistical methods having to deal with biosurveillance. Is anybody out there interested in biosurveillance? Yeah. Or things like drug efficacy testing. I suspect some of you might be interested in that. And Steve's going to talk a little bit about that, but he's also going to talk about a topic that we have not really dealt with in this course, which is designing experiments where the reliability of the system is the response variable of interest. Designing experiments for reliability, like life testing, for example, survival analysis. That's a subfield of experimental design. It's a very specialized topic, and we don't really deal with it in this course. But Dr. Rigdon is one of the leading world's experts on this topic, and I'm so glad that he's going to come And he's going to talk about that. And I'm going to ask him to say a few things about his new book as well, because I've got it, I've read it. It's a fascinating book. And his co-author is a guy named Ron Fricker from Virginia Tech. And Ron has agreed to be a guest as well, but we haven't really got him scheduled yet. It's probably going to be in January. So you're going to get to hear from both of these guys. And Ron is also a very, very gifted statistician that has done a lot of work in biostats and in clinical trial work and in disease surveillance. So you'll find him to be an interesting guest as well. So unless there's anything else, Megan, can we sign off? Dustin, can we sign off?
Yes, sir.
Okay. Well, thank you again for attending. And remember, the Fireside Chats are recorded, and you can go back and check them out on Coursera.